So welcome everyone. Here's another class, and today we'll be dealing with the sound waves. So please get your writing materials ready, and then we'll have a deep dive into the most important points. Might have to touch a couple of formulas and calculations. So make sure that you pay rapt attention because this will be important for you excelling in your examinations. Yeah. So I'll be sharing my screen now, and then we can have a deep dive. So our last class was optical instruments, but now I want to talk about sound waves. Let me see, sound waves. So let me construct the page to my usual notes, and then the white background that will permit us to really discuss in sync with each other. Let me give you the title: sound waves. Sound waves. Sound waves. There you go. Sound waves. Intermediate effect, bounce deep into sound waves. So I'm going to define sound waves first, talk about it. So this is a mechanical wave. Because it requires a medium. Such as solid, liquid. Come and give me a minute. That was a mistake. Solid, liquid, and gas. So sound waves. This is a mechanical wave because it requires a medium such as solid, liquid, or gas, and cannot travel through a vacuum. Take note of that. An additional statement is it is a longitudinal wave whose velocity depends on temperature, wind, density, and elasticity of the medium. Take note of that. Take note of these things. Write and pay attention. The velocity depends on temperature, wind, density, elasticity of the medium. And then we can also make this point. The velocity is independent of pressure. Velocity of a sound wave does not depend on pressure. Another important point we can make is that sound waves exhibit what we call Doppler effect. Doppler effect. And I'll quickly define what Doppler effect is. I'm going to put this in red because it is heavily important. Doppler effect is the apparent change in the frequency of sound due to the relative motion between a source of sound and an observer. Take note of that. Anytime I keep saying take note of that, it is not play. You are in school, you are in college to study. And so when you take note of that, please take actual note of this. This is an examination question. This one comes out both in your multiple choice and in your theoretical questions. What is Doppler effect? Or explain Doppler effect. So please take note of this. You see, between a source and an observer, when you have the change in frequency of sound because of motion, relative motion between the source and the observer of the sound. So generally, I'm going to give you the formula. Generally, what I would call the new frequency. Don't worry, I'm going to give you what this thing stands for. Let me just give you the formula, then I'll give you what each terminology represents. Yeah. This is VS. So this is applicable when you are approaching. Then this is when you are receding. It is the case when you are not approaching, but like moving away from. So when approaching or moving towards. When receding or moving away. So these are the applicable formulas. And what does this formula stand for? I mean, what do each thing mean? What do each thing? I mean, each parameter there. So F prime is talking about new frequency. Just like a question says, find the new frequency, blah blah blah, and then you will know the formula to use. It's talking about the new frequency. Take note of that. Don't worry. By the time we are harnessing these formulas in actual questions to solve problems, they become more understandable. So F prime is talking about the new frequency. F itself is talking about the initial or true frequency. Then V is talking about the speed of sound in air. When you see VO is talking about speed of the moving observer. VS, subscript S, is talking about the speed of a moving source. Take note of that. Speed of moving source. And then we move into, since we're dealing with sound wave, let's quickly go into types of sound. Types of what? Of sound. First and foremost, I will talk about fundamental. Fundamental. You can call it the fundamental notes or fundamental, I don't want to say fundamental sound. Okay, but let's say fundamental sound. So fundamental, most of the time when you hear about sound and they say fundamental, this is the sound of the strongest. Sound of the strongest single and audible frequency. Are you getting me? Yes. So now the next one I will talk about is octave. Octave. Sound. This refers to the sound of twice the fundamental frequency, twice the fundamental frequency. Okay. Take note of these definitions. The next thing I'll talk about is harmonics. Harmonics. This refers to the sound of multiples of the fundamental frequency, the sound of multiples of the fundamental frequency. So, sound of multiples of fundamental frequency. Let's say, okay, let's do this way. E.g., second harmonic is equal to 2 times fundamental frequency. Take note of that. So things like fourth harmonic, guess what it will be? If second harmonic is 2 times fundamental frequency, what's fourth harmonic? You are right. 4 times fundamental frequency. You're doing very well? Yes, that's it. So just get the generalized trend here. That is n harmonic, the nth harmonic. Let me shift this guy. The nth harmonic is equal to n times fundamental frequency. Very good. Let's move to next important terminology. All time in the as regards types of sound is the overtone. Overtone. So the idea of overtones come in when you're talking about the sound of frequency, above and still a multiple. So you say above and multiple of the fundamental. So the idea here is we say you have things like when you start talking about the range of, higher hertz. I mean, like much more beyond the fundamental. Let's say, let me quickly describe one relationship that exists. Okay, I will do this much later. I would establish the relationship between overtones and harmonics. But just get the idea that here you are looking at the ranges of, things like 10 hertz, 20 hertz, 30 hertz, etc. So just keep that in your reservoir for now. Just keep this short and simple. But as we go on, as I deal with, as I do more on sound and musical instruments later on, I will establish to you the relationship between overtones and harmonics. So let's see, the next one is ultrasonic. Ultrasonic. So here we have sound. This is the sound of frequency above the hearing range. The hearing range. For example, we have sounds that exceed that exceed 2000 hertz. So they are used in medical and surgical diagnosis. They are used for testing the quality of the linings and parts in vehicle and aircraft brakes. So take note of this important point. They are used for testing the quality of linings and parts in vehicle and aircraft brake. They are used for medical and surgical diagnosis. So still under the exploration of concept, we are going to talk about beat. What is a beat? This is a throbbing sound. Throbbing, not troubling, no. Throbbing. Throbbing. Throbbing sound produced when two sounds of nearly equal pitch or frequency are combined. Throbbing sound produced when two sounds of nearly equal pitch. That's it. This is the most important concept when you're talking about a beat. Two sounds of nearly equal pitch are combined to give a single common frequency. Take note of that. Take note of that. The next concept is what I will call echo. Echo. Echo has to do with the sound produced after the reflection of sound wave. The sound produced after the reflection of sound wave. It is sometimes, yeah. It is also, let me put, is also regarded as reflected sound wave. So an echo is a reflected sound wave. So we are going to establish some things here. The time taken before an echo occurs depends on the distance away from the reflecting surface. Or a hard wall. So later on, I will establish some formulas when it comes to echo. But for now, let's just leave it at this. Take note of that. So let's go straight into echelon. Echelon. This has to do with the echo. So echelon is a kind of echo or sound heard when the pavement near a fence made of equally spaced iron bars or any series of regularly spaced reflecting surfaces such as a flight of steps is excited. Now, I'm going to explain this idea to you. It says it is the echo you hear when the pavement near a fence made of equally spaced iron bars. So it's either the concept has to relate with equally spaced iron bars or a series of spaced things like a staircase. So if there is any reflection around the staircase or a set of iron bars, you don't just hear the regular echo, you hear something called the echelon. And so I'll go straight into the next one, which is number 9, reverberation. Reverberation. You see this concept of reverberation actively. It resurfaces in examinations. Reverberation. Reverberation. This is the indistinct echo or sound that cannot be distinguished from the original. The original sound produced when the distance from the reflecting surface is less than what is required for an echo. It can be called, so let me quickly give some properties of reverberation. It can be called, so first property, I would say, it is a multiple echo. Continuous. So what you hear is this continuous sound or multiple sound reflection with diminishing intensity. You also have it is the persistent audible sound heard after the source has been cut off. Take note of that. So it's the persistent audible sound heard after the source has been cut off. We also know that it is noticeable in large buildings. So this reverberation concept, sometimes it can be undesirable because let me quickly explain the concept of reverberation. It's a type of echo, and it's like, you getting back, okay, let me use this scenario to describe it. Let's say you have a light hall, and you go inside the hall and you say, Peter, and you hear, Peter, ta, you say, yeah, Peter, ita, ta, you get the idea? Like, that return, Peter, ta, ta, ta. Now, most of the buildings that are large, where music is supposed to be produced, and where music is to be done, this particular concept of reverberation becomes undesirable because, let me write that note. It is undesirable because it causes music and speech to sound confused and indistinct. So that's why you will see in some studios or some rooms, they will put something on the wall. They'll put some pads. They'll put some pads on the wall, like these big square foams. I mean, not normal foams. If you touch them, if you look at them, they look fine, you understand? But if you go and touch them, most of the things there are like foam and, some soft padding. They put them around so to absorb all those things. You see how powerful the concept of reverberation is. So let's go on. Let's quickly talk about reverberation time. Reverberation time. Reverberation time. Let me establish that. Reverberation time. Reverberation time is the time taken for sound of standard intensity to die away until it just becomes inaudible. So it depends on volume of the all. So give me a minute. So try to digest some of the points I'm making. I have to do something. Yeah, go ahead. It depends on the volume of the all. Yeah, so I'm back. It depends on surface area surface area of the walls. The ceiling, the walls, the ceiling, and other stuff. So the surface area of the walls and the ceiling. So let me put that as S. Depends on the volume of the V. Depends on the surface area of the wall, S. And then it also depends on, okay, let me put this as an arrow. It also depends on the sound reflecting properties of the surface. I'm going to call that guy alpha. So sound reflecting properties of the surface. Or this can otherwise be called the average or average absorbent coefficient. Not absorbent, let's call it absorption. Average absorption coefficient. So it depends on these three things. And most of the time when you hear it depends, it's just telling you that the formula is equal to 0.05 V all over alpha S. So this guy is the alpha. So you can see that in the formula, you see volume, you see alpha, you see surface area. So that is the concept. So take note of that. This is the formula. Let me just put it right there. Formula for reverberation time. You see that? So let's quickly talk about something called anechoic or anechoic. Let's put it that way. Anechoic materials. Oh, these are special kinds of materials. Anechoic materials are materials without echo. These are materials without echo. And sometimes people who decide to use other languages, I mean other languages of explanation, they decide to call them soundproof or sound insulation. So anechoic materials they are soundproof. They are soundproof. Soundproof or sound insulation. Sound insulation materials. Examples include glass, fiber, plastic foam, plastic foam encased in muslin, that is spelled M-U-S-L-I-N, muslin and leather panels. So any of these materials, they can be used. They can be used in a recording studio. You know what I mean? Like in the concept I explained initially, where I was explaining, I said in order for you not to have reverberation, where you have Peter, you use some of these materials like the glass, the plastic foam encased in muslin and leather panels. You mount them at strategic points in your recording studio, and then they are able to absorb sound. So they don't permit echo. They're soundproof. Yeah. So let's go straight into another subtopic, and that is the applications of echo. Excuse me. Please, no jokes, no jokes. You can, just laugh for a bit and keep walking. So there's no room for seriousness. Applications of echo. They are used for measuring the depth of the sea. So there is something called the echo sounder. Using echo sounder, I can call it a photometer. And hydrophone. So take note of that. So it's also used for underwater exploration. One of the projects that I did as an undergraduate, I was trying to look at the seismic attenuation with the sedimentary basins and the basement complex of Nigeria. And that concept involves the use of waves that are kind of similar to sound waves when they propagate through the head, and then you are able to measure how they are able to penetrate the earth. Now, why am I talking about this concept? When you want to look for materials or you want to see how possible earthquake occurs in a place, you use some attributes of sound. And also when you want to probe water, when you want to explore water resources, I mean like the ocean, the sea, I want to see what's happening. You don't necessarily want to go too deep and send human beings there. You can send sound. Underwater exploration for gas. After you've established some theory, by the time the echo does this and gives this kind of feedback, I know that gas and oil is there's a high propensity or probability that there is gas and oil in this particular part of the sea, or something must have happened. God forbid that we have bad occurrences, but there are some times when you have cases where there is capsizing, a ship capsizes and they don't even know. They are trying to locate where it capsized. One of the concepts they use is this concept of sound, and they're able to know, by the echo and all of that, the technology involved, which is primarily founded on echoes, they are able to locate where shipwreck, exploration for gas and oil, or shipwrecks, where shipwrecks have occurred. So just, get familiar with this concept for the purpose of knowledge and also to excel in your exams. you have to study and make sure that you go beyond this level because you want to advance in life. Determination is also used for determination of speed, of sound in air. Yeah, you can also use it to determine the speed of sound in air. You can use it for the location of shells of fish by fishermen. Yeah, can locate shells of fish. So for most of these, when you want to make use of echoes and all of that stuff, the sound that we use most of the time to apply echo, to apply the concept of echoes, Ultrasonic. Ultrasonic sound is mostly utilized. That is when we are talking about the sound that we use to probe water bodies. We're not talking about your normal sound, like just the normal that you hear, no. Very, very loud. Well, let me just place the characteristics of ultrasonic sound. Ultrasonic sound that utilized, that sound of short wavelength and high frequency. Please take note of that. We now go to talk about a very important concept, which is the determination of velocity of sound in air. And I will look at different cases. The first case I'll look at, which can come out in your question, is the case of reciprocal firing. Reciprocal firing. Reciprocal firing. Let me put a formula down before I let me put a formula down before I write some note on it. So we can have, when we have reciprocal firing, we have if we have one time at a time, let me put it this way, at a single time, you just calculate V as X over T. But when you have two times, do it like this: 1 over 2 X over T1 plus X over T2. So just keep that in mind. Echo method. Let me talk about echo method. So for echoes, you find velocity with 2x over t, where x is the distance between sound source, and reflecting surface. And t is simply time. We already know t. It's time involved. And let me quickly note that you see that distance 2x, it can be asked from you. What does it mean? It means the total distance traveled by sound before the echo is heard. Think of that. Don't worry. For most of the physics that we do, we kind of establish, we give you formula space. Then when we start racking our head with questions and problems, you will see how important those formulas come to, what they bring to the table. So let's quickly dive into the factors affecting velocity of sound. Factors affecting the velocity of sound. In this, we are going to talk about the first thing, temperature. How does the velocity of sound, how does it vary with temperature? So the important point here is that velocity is directly proportional to the square root. To the square root of what? Of temperature. So make sure you write that properly. Directly proportional to the square root of what? Temperature. And what does that mean? V is directly proportional to square root of what? Temperature. It means that as velocity increases, temperature increases. So you can just put it like that. As velocity increases, temperature increases. One of the important points here is directly proportional. So as velocity increases, temperature increases. Take note of that. Is that okay? Yes. The next factor, which I will say velocity of sound depends on, is density. This is temperature. Is density and humidity. Density and humidity. As for density, V is inversely proportional to the square root. Or you can say it varies inversely with the square root of density. Or you write it this way. So just keep in mind that this is the relationship. This is the relationship between. So, and the meaning of that is velocity of sound. Let me put it like, as velocity of sound increases, density decreases when you hear inverse relationship. So I'm going to write it as inversely proportional to the square root. Of density. I'm quickly going to give you the physics of this thing now. Now, if I ask you on first approach, if I say, oh, you are in a physics class and you've been learning a couple of things, I think if you've taken my class on refraction, you would have heard me talk about the movement of light from a less dense medium into a dense medium. And if you remember very well, when talking about a less dense medium, I was talking about the movement of light from air into glass. Now, in terms of density, which of them will you say has the highest density? Which of them is more dense, solid, liquid, or gas? The answer is solid. Solid is more dense, more heavy. Followed by what? Liquid. Liquid is also heavier than what? Gas. So the least dense, the one with the smallest density is what? Gas. The one with the next one is what? Liquid. And the one with the highest density is what? Solid. If sound is inversely proportional to square root of density, I mean, if the velocity of sound, the speed of sound, if it's inversely proportional, that is, as the density increases, the speed of sound reduces. It means sound is fastest in what? Where is sound fastest? Okay, let me write something to solid as the highest density. So the more the density, the lower the speed of sound. Why? Because we have said as velocity increases, density decreases. Or you can say as density increases, velocity decreases. They just do opposite. So they have the opposite relationship. So if it's solid, solid has the highest density, so it will have the lowest speed of sound. You can say opposite relationship. So it has the lowest speed of sound. When we say speed, we're also talking about velocity. I mean, at least in this concept. You understand? So liquid is next. Why gas or air has the lowest density. So it has the fastest. So it has the fastest velocity of sound. So if in a OBJ question, you are asked, which of the following, in which of the following is sound fastest? Your answer should be gas or anything that tends towards air or something. So in which of the following is sound slowest? It should be anything that looks like a solid. You understand? So that is the gist at this level. Then when it comes to humidity, because this particular point was saying density and humidity, velocity has a direct relationship. Velocity of sound is directly proportional to humidity. So we're saying V directly proportional to H. What's the meaning of this? The higher the humidity, the higher the speed of sound. The higher the humidity, the higher the speed of sound. Take note of that. And what is humidity? Most of the time, we define humidity as the amount of moisture in air. So take note of that. Let's go to the third factor, elasticity of the medium. Give me a minute before I discuss that concept. Use that minute to catch your breath. I might have a little correction to make. I want to confirm something in my note. So catch your breath. So the question I'm asking in my mind is, by general belief, it is noted that sound is fastest in solid. So, but then solid has the highest density. Let me clarify that. This is a good time to have critical thinking. Hmm. 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 Wonderful. I want to re-explain the concept. So let me just remove this particular section that I talked about. Let me delete that. No, let me go back. Because I want to explain it from another perspective. So before I go, I really just hope that you have not, but even if you have, it's a good time to have some real critical thinking. Let me tell you the question I asked. And maybe we'll just do a little thing after this, and then we'll call it a day in this class. But this is super important. Yeah. By the laws of physics, by the laws of physics, we said the velocity of sound increases as density decreases. Now, but then, generally, sound is faster in solid than liquid, liquids, and then gas. That is, it is fastest in solid. Then liquid are faster, then faster in liquid than gas. That is, the highest is solid, then followed by liquid, and then gas. Now, if we were to explain it just by density and say, okay, solids are more heavier. So since they are more heavy, they should have the slowest, just like what I said before. They should have the slowest, sound should be slowest in them. No, I'm going to explain why it is reversed. Now I'm going to explain this. Let me take that out. By the formula relationship, by this formula relationship, which says that velocity should be, velocity of sound should increase as density decreases. That is an established formula. As should increase as density decreases. That's established formula. But we see something that happens in reality. Because now, I'm taking it at each level, step by step. But there is a general formula that relates velocity to a number of other things. So by the time you look at, you combine all the factors, some of them balance each other. So at the end of the day, let me explain. In a solid, we have, most of the particles are very, very close, very, very close, very, very close to each other. In a liquid, they are more loose. Then in air, they are very loose, they are very spaced out. So the concept of speed of sound is such that when sound wants to pass through a solid now, it is very easy to transfer the energy to each particle because they are close to each other. So it will quickly pass through. It will pass through them because it will quickly transfer to each other. But when it goes to a liquid, it will be slower because the particles are not so close. It takes more time to touch each other. You get it? So it will pass through at a slower rate. But then when it gets to air, the particles are more spaced out. So it takes longer, even longer time to transfer the energy through each of them. And then it will pass through at a very, very much slower rate. So the concept of density is now talking about, I'm relating it to like how close the particles are. Normally, this by formula, keep this in mind and keep it standardized. By formula, this is the relationship. It is inversely proportional to the square root of density. Keep that in mind. And that means as density decreases, sound increases. So, but then when you now consider reality, the ideal case, when you take a solid and you take a liquid, and you are saying, okay, I know that a solid is more dense than a liquid, and a liquid is more dense than a gas. Why then does sound travel faster? You see, when I was thinking, this is critical thinking, I took some minutes to hold back and say, oh, by general belief, because I made a mistake that time when I said sound is faster, sound is slowest in solid. No, by general belief, sound is faster in solid. And I'm asking that, based on density discussion, this should not be. So what is actually happening? And that's where this discussion of the closeness of particles. So what explains that is what? The closeness of particles. And then the reduction of time to transfer energy. Between them. So keep that in mind. So generally, sound is faster in solid than liquid and then gas because of the closeness of particles and the reduction of time. So it's not necessarily by the density explanation, because the density explanation will contradict. That was why initially I had already established that sound is it is slowest in sound. No. The actual reason to explain why it is faster in sound is because the particles are more closer, and that's how it works. So keep that in mind. But as for the relationship with density, this is it. So let's go on into elasticity. So I needed to establish that. So please, let me put this in red. Generally, sound is faster in solid, followed by liquid, and then gas. So if you have an OBJ question, I'm reiterating now, correcting what was initially established because of that direct twist with density. No, there is a much deeper, like I said, as we go on, you will see a comprehensive formula that relates to velocity. Please just take this thing as a learning process. You should be willing to learn, unlearn, relearn, and process. And you should not even know why you are doing what you are doing. I've established to you that, if we are to just jump in by the explanation of the velocity of sound based on density, we are going to make the wrong decision of saying, since solids are more dense than liquids, they should be, have a higher. But no, by actual physics, because the particles of solids are closer, sound tends to transfer the energy quicker between them. And so we have a higher speed. So this density relationship is more of something that, will be influenced in the comprehensive formula. So it's more something that you need to know. Will I call it abstract learning now? Or it's not something that explains, it's not something that you will relate directly to this. for now. Just keep it in mind as the relationship with density. But it does not explain why sound is faster in solid. What explains why sounds are faster in solid and then liquid and gas is the concept of closeness of the particle and reduced time. So if you explain sound being faster in solid from the perspective of density, I mean just superficially by saying, oh, since it's more dense if since solids are more dense than liquid, you are going to misexplain it just like I did before correcting myself. So keep this in mind as you read. Make sure that you are doing great in understanding this particular part. Let's go straight into another factor, which is elasticity. Elasticity of the medium. So, and here we'll have three different parts. For solids, velocity varies directly as the square root of the elasticity for solids. For liquids, velocity varies directly as the square root of Buck modulus. E here is Young modulus for solid, Young's modulus. So K here for liquid is bulk modulus. And then for gases, velocity varies directly as square root of a coefficient multiplied by pressure. So that coefficient is called the ratio, something like a mu, ratio of specific heat. And then P is the pressure. So keep all of these concepts in mind. And then when we talk about the general formula, we write it for solids. Generally, for solids, we write velocity E over density. Then for liquids, we write it as a K over density. Then for gases, velocity is that coefficient multiplied by pressure over density. So keep all of these concepts in mind. I will now go to the next factor, wind, which is where I will end today's class. Let's see. Velocity increases with wind coming from the source to observer. So let's just say velocity increases with wind in same direction. That's a good way to put it. If the wind is in opposite direction, it will reduce the speed of the sound. But if the wind is in the same direction, yes, kudos. Velocity increases with wind in the same direction. In the same direction with sound. So please keep all of these things in mind. A good note is that in all of these factors that we mentioned wind, we mentioned elasticity of the medium, we mentioned density and humidity. And then again, let me quickly put here, velocity varies directly as humidity. Humidity. Yes. Density and humidity. So the idea here is we don't just consider density individually. Humidity is more like, you see, humidity is the amount of moisture in air. So as the amount of moisture increases in air, you discover that air particles, they are no longer, so spaced. Like there's now like moisture there. Moisture increases the number of particles there, and so things are more close. molecules and particles are more close, so they can easily transfer energy. So velocity increases with humidity as well. And then take note of density. So we mentioned temperature, density and humidity, elasticity, wind. But note that pressure alone, pressure as a single factor, has no effect on velocity of sound. That is when you just consider pressure alone. So that is, pressure standing alone does not affect the velocity of sound. Please and please keep that in mind. So when next we meet in this class, we'll talk more and probably solve more problems on sound waves and, enlighten ourselves. So please keep the critical thinking energy high, study, and, understand as many things as you can so that you do great in your exam. I'll see you in the next class, and goodbye for now.